Okay, so this is the first of the two videos for week 4. And we are getting ourselves into talking about the techniques of data mining. Okay. And so the first technique we're going to look at is what's called cluster analysis. In this first part of the lecture, I'm just going to talk about the theory of cluster analysis. And then the second part, I'm going to talk about the techniques we're going to use. I'm going to talk about something called unsupervised algorithms. This sort of comes from machine learning, which there used to be a machine learning course, and basically the content was almost the same as this. So I got rid of that to replace it with data mining. But when you have a data set, you may or may not have something that's called a label. A label can be thought of as a tag. Typically, a label is just a categorical variable with a finite set of values. Something like yes or no is a good example of a label. Is it a tree? Yes. Is it not a tree? No. But not all data has that. So example of labeled data, this is my creative work here. Items in a grocery store and then the categories, because items in a grocery store can be labeled with the category, and the category is the label. So, but if we didn't have this category column, we would just have the items, okay? And we would therefore have unlabeled data. So labeled data, you have some type of like short categorical variable that clearly can serve as a tag or identifier to what the data is and belongs. When you have labeled data, you do something called prediction and classification. That is the next 2 weeks, but not this week. And these are the techniques we'll look at in the next 2 weeks. Okay. These methods that use labels are referred to as supervised learning, because the labels supervise the learning, because what you do is you have data and you know that a cilantro is an herb and a tomato is a vegetable and a butternut squash is a vegetable, zucchini is a vegetable. And you use this category to, quote, train a model, and we'll explain more about that later. But you have this pre-existing category, and that's what's important. So you have this category to supervise the training. With unlabeled data or unsupervised learning, you don't have that. So this week is about unsupervised, and next week is about supervised. When you have a label, you can use classification and prediction. That's next week's stuff. When you don't have a label, what about data that has no labels? A lot of data doesn't, particularly data that's novel or recently collected. You will not necessarily have like a categorical variable that can serve the function of a label. Not every categorical variable is a label. To be a label, you have to be something that's sort of like a unique kind of like group identifying or yes, no. Binary yes, no can be a label, but you have to have something that's not just a categorical variable, but serves to be able to classify and train data, which is the next stuff. But if you don't have a label and you have novel data, how can you actually go about creating a label? So the first step is to work with what you call unlabeled data like this. Now, this is a good example of unlabeled data. It just has 8 binary variables, but there's no identification in terms of none of these variables serve as a label because we don't even know what they are. They're just 8 variables. So nothing would be known about how to group or organize this data. And this is what we would call unlabeled data. Okay. So if you have unlabeled data, you use what's called unsupervised algorithms. That is the language of machine learning and AI, not so much data mining. Data mining, you just look at the techniques. But unsupervised means that there is no label in the data. So there is no short categorical variable that these data values can be classified as. We don't know. So working with unlabeled data is often a precursor to labeling it. So it's kind of like the first step, which is why we're doing it in the beginning. Okay. And so for unlabeled data, we're going to use what's called unsupervised algorithms. And the purpose here is to discover structure in a data. Remember that data mining is all about finding patterns and stuff. So data mining is often a very exploratory technique. You do data mining before you do other things with the data. And so one of the first things you can do if you have a bunch of data that you don't even really know necessarily so much what the different columns are, how they relate, you want to start looking for patterns. And so this week is kind of the beginning of the pattern hunting. Okay. There's two types of what we call unsupervised data mining. One is clustering, the other is association. Now, clustering we're going to do this week, and then association we're actually going to do week 7. So clustering is literally what it sounds like. It's clustering things together. It's based on looking at the similarity of the data, and we're going to measure similarity in terms of mathematical distance, which is not something that's that hard to do. And it will discover the structure of the data by comparing how mathematically far away the different values are. Okay. So the first thing we have to learn to do is we have to actually learn what this means to calculate mathematical distance. Okay. And you've actually done mathematical distance if you ever took math beyond 7th grade, because something like the Pythagorean theorem that turns into the distance formula, that literally is mathematical distance. So we need to learn and review how to look at mathematical distance. So clustering is an unsupervised method of data mining that relies on grouping together data based on distance metrics of similarity and difference. First, the concept of mathematical distance is reviewed. Distance literally is what it sounds like. It's how far two things are away from each other. In physical space, distance is the shortest line between items, right? So I drew this myself. It's a block and an oval, and then the shortest line between them. This would be the distance. You can measure distance. At some point in life, you learn how to use a simple little ruler, and you just measure things. And when you're measuring, you call it length if you're looking at something short, but really that's distance as well. So between, to look at how far things are away from each other, that's called distance. If it's within the same thing, it's called length. But that's what distance is, simply put. Okay. Then when you were in algebra in high school, you started looking at the XY plane, and then you can look at 2 points on a plane, and you can measure the distance between the 2 points. So for example, if I had point 1,1 and 1,4, these would have a distance of 3. Now these are they have the same x value, so you can, it's just 1, 2, 3 up the y-axis. You don't need to look at the Pythagorean theorem quite yet. Okay. Then if we go to 2-dimensional distance, you have x and y, and you look at, in the Pythagorean theorem, this is called a and b, but the distance formula comes out of the Pythagorean theorem, and you look at a squared plus b squared, which is what this is, and then you take the square root of it, and that's the value of c, which is the length of the hypotenuse. Okay. So that is what mathematical distance is, and this one is called the Euclidean distance. There are others, and the Euclidean distance is it's basically the Pythagorean theorem and renaming it as distance rather than the length of c, and that is the distance formula. Okay. So here is an example of my fine artistic work here, and this is a Cartesian plane, and there's 2 points in the plane. Let's go back. Spilled the beans here, right? I did something weird to the slide, so you do that first. But anyways, so here we have the point 1,4, and then we have the point -4,1, and you plug the values into the distance formula, and then take the square root, and you get the distance of 7.07. And literally, I have just told you what mathematical distance is. It's pretty easy, actually. This, however, of course, is algebra class. Algebra, everything is abstract, and you talk about x and y on a basic Cartesian plane. Data, though, is just an expansion of this. Right? In algebra and geometry, you talk about distances being xy plane, but bivariate data, it's variable 1 and variable 2. And it's the same exact idea. So literally, when I talk about measuring distance of data, this is what I'm talking about. Okay. You can also do this in x, y, z. You can expand the distance formula, and you can do basically the same formula in 3 dimensions. Okay. And that's important because with data, you very often have more than 2 dimensions. So you want to look at the distance between points. Now this is like column X, column Y, and column Z. And you want to look at the distance between variables that now have, data that now has 3 variables, and you have to use all 3 variables in the distance formula, and so this is how you would do it. But then, wait, there's more. Now, I am sneakily changing things here. I'm calling this, instead of calling this x1, y1, z1, because in the Cartesian plane this would be x1, y1, and then z1. Or Cartesian, not Cartesian plane, but Cartesian like space, you would call it, because now it's 3 dimensions, it's no longer 2. So this is point 1, which was x1, y1, z1, and I'm renaming it as p1, p2, p3. And then I have q, which I'm renaming as q1, q2, 3. And then I'm rewriting the distance formula as this. Okay. But you can still calculate the distance between these 2 points very easily with this little formula. Okay. So why am I telling you this? Because now we can also expand this to the nth dimension. So this is 3 dimensions. We can't make a plot beyond 3 dimensions. It gets wacky. You can't really visualize it. So beyond 3 dimensions, humans really can't experience the physical world of 4th dimension beyond. However, in data space, you can, because data, in a data set, dimensions is a number of variables. Right? Cursive dimensionality from last week, too many variables. But you can have as many variables as you want. It's theoretically infinite. I mean, at a certain point, your data becomes almost impossible to work with, but there's no limit. So what this does here is it takes this formula here, right? 3rd dimension, 2 dimensions, 1st dimension. But you can keep expanding this out, which is why I rewrote it like this. And you can expand it to the nth dimension. And then when you do that, you will have this formula, and it would be 1st dimension, 2nd dimension, where k equals 1, 2, 3, 4, 5, 6, 7, 8, 9. And you can calculate the distance between any 2 points, regardless of the number of variables, using this basic idea of Euclidean distance. Okay. And you can, this is the most commonly used distance metric of all time. There are others, but realistically you won't use those, except in weird situations. So, but the Euclidean distance metric can be used to determine the mathematical distance of any 2 data points with any number of variables. Trust me, it's possible. Okay. So other distance metrics, the Euclidean is actually a general, it's one example of something called the Minkowski distance, which admittingly I studied in grad school a million years ago and have never really totally used. But there are other distance metrics. There's something called the Mahalanobis distance, which this one, if your variables are correlated, remember the cheese example? Those variables were sort of correlated. When we looked at them, they had linear patterns, kind of like in the scatter plots. And so if you have variables that are correlated, you might actually want to use the Mahalanobis distance and not the Euclidean distance. You don't actually have to know the formulas for these, because the way you're going to use these is in the software, it will calculate them for you. I mean, nobody would actually want to calculate distance with a huge data set by hand. That would be crazy. Then there's something called I think it's pronounced Jaccard, I don't know. Jaccard distance. This one is used when the variables are binary. And that means data sorry, I'm going all the way back here. Binary means data like this. These are binary, 0s and 1s. And binary is very, very common to have because yes, no data, if people answer questions, that is binary data, right? You can think of it as categorical or binary, but when you have binary data on something that's yes, no, you can calculate distance metrics on that with this Jaccard one. You wouldn't want to use Euclidean distance for the binary data, but this other distance metric that I'm not super familiar with, except that it's an option when I click things. This Jaccard distance is something to note because you can use it on binary data. Okay. And there are several other metrics. Admittingly, I don't know a lot of them. I did work with Mahalanobis in multivariate stats in grad school. Okay. So let's actually watch this in action. Here is a really simple data set made by yours truly. So we have 4 observations and 2 variables, x and y. Okay. This data, I plotted it, A, B, and C, D. I'm just plotting these points, X, Y, just like you would in algebra class, okay? So then if I were to actually do this by hand, and I did, going and hanging out with Euclid there, so you could do the distance A to B. Now this is 0, 1, 2, so this is just 1. And then also I did the actual distance calculation for A to C with the Pythagorean theorem distance calculation thing. And I literally actually sat there and did all of these by hand. Well, sort of it by hand. I did them in Excel. And these are the distances I got. So like B to C, I got 6.08. So this is B and this is C. I got 6.08. And then C to D, I got 1.4. So that's that. And I double checked these. They were right. And so I actually calculated, there's 4 points. There's 1, 2, 3. There's 6 different distances. The distance from B to C is the same as C to B, so I'm going to count that once. You know what I mean? The direction doesn't matter. It's the distance from here to here. And then like D to A is 7.6. Okay. So that would be that one. That's the biggest one. Right. And so I just did these all using using this, the basic distance formula. These only have 2 dimensions, so I didn't need to go to here. And then nth dimension, you go to use this formula. But it's pretty easy to just, I mean, you could do all of this by hand if you wanted to, but that would just be nuts. I mean, I did do this by hand because it was over the summer and I was bored and I had nothing to do all day. But anyways, now I'm jumping to this and you're like, what is this thing? This is actually a very important thing in this course. This is called a distance matrix. On the rows, we have A, B, C, D, and on the columns, we have A, B, C, D. The diagonal is all zeros because that's the distance from A to A, which is nothing because A is A, so you don't have to go anywhere. B to A is A to B, which is 1 and 1 because they're the same thing. See that? Then we have, hopefully not a dying computer. I didn't check if my battery was dead or not. I should probably check that because it's acting like it's about, no. Yep, it is. 2 seconds. I gotta change the battery. Okay. Sorry, I had to plug in because otherwise it will go battery dead in the middle of my video. That would not be good. I know there's a button that says start from current slide, but I always ignore it and I always start from the beginning by accident. And anyway, sometimes it's good to flash through things. But anyway, so the distance space is here, and all this is doing is visually displaying the distances in a way that is easier to read than plotting everything out like this. So like A to C is 6.32, and this came from here, right here. So, but one thing you can see in this is that you don't need both this part and this part because they're symmetric across the diagonal, so you can either use the top one or the bottom one, but there's really no reason to do both because they're completely redundant. Sorry. Anyways, and so whichever way you want to simplify it, it doesn't really matter. You can do the full display or you can do half the matrix. Okay. Software will, of course, create this thing for you. You would not want to do this by hand. Most data mining software will do a distance matrix, which is one reason why you want to use sort of data mining software and not like Microsoft Excel, because I'm pretty sure Microsoft Excel will not do anything like this. Maybe if you have like Excel Miner or something plugged in, but typically, in order to start doing the type of stuff we're going to do specifically for data mining, you really do need the specific software. So to do a distance matrix is really, really easy if you have the right software, and it's really, really hard if you don't. So look over the distance matrix is really good practice before doing anything else. And yeah, but back to this idea of normalization. Last lecture, we talked about how to normalize data, meaning standardizing it to the standard normal z-score 0, 1 stuff. So that lecture is still available. Go back and review that, what that means. I told you that most of the time in data mining, in fact, for you guys, just all the time, you really want to scale your data to a standard normal, and here's why. Scale refers to the measurement scale. That's like inches, dollars, centimeters, whatever. The problem with scale is that it affects the distance. Okay. In algebra and classes like that, we don't care about things like this yet. So this kind of issue of scale impacts sort of like is kind of like new. If I weigh 180 pounds and you weigh 160, the distance between our weights is 20 pounds. But if I weigh in kilograms and I just converted the same thing, so I converted 180 to 80 pounds to kilograms. If I weigh 81.6 and you weigh 72. If we do this in kilograms, the distance is now 9. So it's the same us. It's you and me, and it's the same weight, but the weight's in different units. So if we do this, we have a 20 difference. If we do this, we have a 9 down. But when you look at distance, often you don't even include units. So this is what I'm talking about in terms of scale affecting distance. Okay. You don't want that. Okay. So you want to get around that problem by doing z-scores. So here is the normalization, which for pretty much, there are actually other things called normalization and standardization. When I say normalization, standardization, I am referring to transforming your variable with z equals x minus mu over sigma and making it a z-score on the standard normal. Okay. This again, same slide as last week. Standard normal, same slide as last week, convert to z-scores. So most software will do this extremely easily because if you're using the right software, which is why you want to use data mining software and not like sort of general stat software or Excel or something, or like Tableau and stuff. Because Tableau actually might give a distance matrix, but it's just a lot easier if you have the right software, which is another reason why in data analytics we use different tools, because different tools are good for different things. So let's consider converting these guys. Okay. Let's convert these to standard normal scores. Okay. So when I do this, this is the same stuff. Height and weight, and I never actually use the, I actually did this in inches and pounds. I did height and weight here, not just weight. But anyways, if we do it in inches and pounds, the distance is 20.1. I put it x and y, and so I didn't just do this one. I just did one of the variables. This one I did the height and the weight. So I have x and y. So if I did x1, y1, x2, y2, and then use the Pythagorean theorem, I get this. Pythagorean theorem distance formula are the same thing for all practical purposes. Anyways, and then if I did it on these scales, I would get this. So I get two different numbers even though we're the same people and we're the same height and weight. If I standardize, and to standardize these, this is the mean and standard deviation. So to get this, I would do 66 minus 64 divided by 3, because this is the height one. So 2/3, I run it off to 0.7. So these are the z-scores. Okay. And if you notice, of course, the z-scores are the same. So here, our numbers are all different because we're on different scales. When we go to the z-scores, we get the same thing and we get consistent distances. That is the point to standardizing and normalizing your variables, and it's really important to do that in data mining, especially when you're working with something like distance. There are some things in data mining that it's different because you're not working with distance, but we're doing clustering this week, and all of clustering is based on distance and similarity of the data, and you want to standardize it. You do, trust me. Okay. So with the standardized data, the distance metric is stable. They are the same. And the scale of measurement is not affecting them as it is here. So that, I hope, is a good illustration as to why you standardize things. A lot of professors will just say, hey, standardize your variables, and not really explain what that means. That's why we do this. Okay. Normalization matters because data mining algorithms such as clustering analysis are based on distance. The whole business of clustering is based on calculating distance between points, aka rows in the data. Okay. And the results can be very distorted by the measurement scale unless you use normalized data, in which case it will not be, which is what you want. Okay. And that is the end of the first part of the lecture.